Hi everyone, thanks for watching this video, and let me begin some important remarks on the exercise class. I want to kindly remind you that please follow your emails regularly from the assistants, and in these emails please find the link which is given over Google Documents, and in this file actually you are going to see two sections, and one section is about your questions on the homework questions, exercise sheets, and the other section is about your suggestions. And as a response of one of the suggestions, we created doodle poll, and please visit that doodle and pick all possible dates for the next week question and answer sessions. And the last but the least, please contact only with your TAs, and we thank you for your cooperation. So okay, in this week's homework questions, in the first exercise, we are given 7 statements and we want to decide if they are true or false. And in the first statement, we have a matrix which seems a kind of spatial matrix, and it is claimed that f of x is minimal polynomial. So to decide it, we recall the definition of the minimal polynomial. You can also find the solution manual of homework 2 and the lecture notes. And briefly we need to check a couple of items. The first one, f should be unique. This is true because the leading coefficient is 1. And the second one is f of a should be 0. Yes, this is also true because we can easily see that f of x is the characteristic polynomial of a, and by Cayley-Hamilton theorem, we always have that a is a root of the f, its characteristic polynomial. And finally, we need to decide f is the unique polynomial with the smallest degree, which this property. And to say this, suppose not. So we assume that there exists a polynomial g of x of degree at most 2 with some non-zero coefficients such that a is also root of this polynomial. But on the other hand, particularly if we consider the column vector with these entries, on one side we see that the matrix multiplication is going to be 0 because g of a is 0 by the assumption. But on the other hand, when we really compute this matrix multiplication, we obtain these coefficients. So actually this is a contradiction because by the assumptions we pick these bj's as non-zero. And moreover, to say the uniqueness, by the way, this concludes that the degree of the minimal polynomial cannot be less than 3, so it should be 3. And moreover, if there is another monic polynomial of degree 3, such that g of a is 0, and we also know that from the second item there's a f is also such a polynomial with this property, and by solving these two equations we conclude that actually this polynomial is exactly the same polynomial given in this form. So we conclude that the statement is true. So for the second statement, we have a set. Actually, this is a subset of all diagonalizable matrices. And we want to see that actually it is not a commutative group. Actually, it is even not a group. And one axiom fails. And this axiom is that not every element has a multiplicative inverse in the set. We may easily see by the counterexample, we fix the invertible matrix P as an identity. So in this case, whatever we pick S from this SP, S is going to be ds. But we can easily see that the diagonal matrix with the 0 and 1 entries on the diagonal lies in SP, but S is not invertible with respect to matrix multiplication. So this is not a group. And yes, the third and the fourth statement, I mean, almost the same, but the only difference is the base field. So in this statement, we want to understand what's going on when we fix our base field as real numbers. So we always know that the dimension of a vector space and the dimension of its orthogonal complements, sum of them, gives us the dimension of the whole space. This is 3. And we need to see this intersection is trivial. To see that again, suppose not. So that means if this non-zero vector lies in this intersection, it should be self-orthogonal with respect to this bilinear form. But on the other hand, for non-zero real numbers, we always let their square are strictly bigger than 0. So we have contradiction. So that means we have trivial intersection and this sum is direct. But this is not the case for the statement 4. And here please note that in this finite field, in this world, 1 plus 1 is equal to 0 in F2. So this allows us to create an example. We can consider a vector space. Please see that this is a subspace of F2 to the 3. And we also see that this vector is self-orthogonal with respect to this bilinear form. So that means it lies in the intersection. That means this intersection is not trivial. So this statement is false. So for question 5, I want to explain, okay, this statement is again false, but I want to give a counterexample on the specific case. And in this case, I want to fix n as 2, and I choose the base field as real numbers, and I will consider a linear map, an endomorphism, which is defined with this matrix multiplication. But when I consider the standard basis, they are going to be orthogonal to each other. But for an invertible matrix, we see that orthogonality is not preserved anymore. So this statement is false. So in the last two questions, we have two different vector spaces. And in the first one, our vector space is the n by n matrices over K. And we want to see that this map, this transformation, lies in the dual space of this vector space. So to see that, okay, obviously, I mean, what is the definition of this map? You have n by n matrix, and it's taking trace. It has a spatial name which is called trace, and the image will be the sum of the diagonals. And it's easy to see that this is a linear map. That means we always this equality for all n by n matrices and the constants alpha and beta. It shows us trace is in the dual space. But this is not the case for the statement 7. And to see it, we want to consider some differentiable functions, and one of the nice and the easy candidate are the polynomials. We consider two polynomials in this form, and f plus g can be defined by the pointwise, and we see that linearity fails. Yes, this is true because the image of the f plus g is going to be 2 times 0 plus 1 times, when we evaluate f1 we obtain 3. But on the other hand, when we evaluate f and g separately, we see that the right hand side is going to be 0 and they are not equal to each other, though this statement is false. And yes, this statement is true. So, okay, hope to see you in the next video. Bye.